Let's talk about Newton's third law. This is the reading assignment, the homework that's due not Monday. I guess we have clear till Wednesday morning because of the holiday on Monday. And in order to talk about Newton's third law, well, first of all, you've all learned Newton's third law in high school or junior high. What is it? What's the thing you memorized? Equal and opposite. Okay? For every action, there's an equal and opposite reaction. I hate that wording of Newton's third law. I'll explain why as we go on, but that's what everyone memorizes. And in order to understand this concept of equal and opposite forces, we have to really understand what a force is. And so we're going to operationally define a force. Before we just kind of waffled and said it was going to be a push or a pull. Perhaps we could use Webster's. This is what we find in Webster's dictionary. Power of energy, strength, the force of a gale. Power exerted on any resisting person or thing. What do you think? Should we use that one? Definitely not. Okay, there are so many words in that definition that are tied to other physics concepts that makes this definition totally worthless for our class. Here's another possibility. Trust the force, Luke. Well, it's kind of a dark picture of Yoda there. But again, we're not looking for anything mystical here. Okay? It's much more straightforward than that. It's a push or a pull, but we're going to come up with a recipe for actually getting a number for this push or pull. First of all, let me just mention that a force we will define as something that acts on an individual object. And what do I mean by that? I mean, if I happen to slug Chris here, boom. As I slug her, there's an interaction going on between my fist and her jaw. Okay? But we're going to break that interaction apart into two forces. One force is acting on Chris. The other force is acting on what? My fist, yeah. Okay? And we're going to treat those as separate forces. And the direction of that force, just use your gut. You know, if I came and swung, the force acting on Chris's chin was clearly in the direction that the hit happened. You know, you don't need anything sophisticated to define the direction. To get a magnitude, to get a number to go along with that, it depends on whether we're talking about a push or a pull. If we're talking about a pull, if I were to reach over here and let me just grab Sarah's hand. If I wanted to measure how hard I'm pulling on Sarah's hand, what I would do is I would insert a spring scale and do exactly the same, do exactly the same thing that I did before until it feels like I'm pulling just as hard as I did before. And now, the reading on this spring scale, I will define operationally to be the magnitude of the force that I was exerting before. Now, with a push, this is just not going to work. You push on these and you don't get a reading. Only with a pull do you get a reading. So if I push, I'm going to use a different operational definition. Bathroom scale. Okay? And now, if I push on this wall, and I wanted to operationally define the magnitude of that push, what I would do is just slyly slip this. Slyly is the key word there. Slyly slip that bathroom scale between my hand and the wall, push the same way I was before, and the reading on there, which is 19, would operationally then be the magnitude of the push. Now let me ask you a question. Suppose I'm pushing on this and I have a push that reads here 32. And let's suppose that the wall did really have eyes and could see. And suppose that instead of this bathroom scale being the way it is now, it were somehow magically flipped so that I couldn't read it, but the wall could, if the wall had eyes. What would the wall then read? 32. Yeah, that's not much of a stretch. Okay, I think your gut tells you that it's going to read 32, whether it's facing towards me or whether it's facing the other way. And that is going to be very important when we talk about collisions. And I just happened to have some pictures of a big truck and a little car. And let's suppose that those two came and had a head-on collision in which no one was hurt. Okay? Now, before we had PowerPoint, I used to always draw pictures of cars colliding, and I always use Volvos because no one gets hurt in a Volvo. Besides, they're boxy and I can draw them. Let's suppose that these two come and they collide, and the question that you were asked on the first day of class is, which is going to exert the bigger force on the other? Is the truck going to exert a bigger force on the car or the car on the truck? Maybe I didn't tell you enough information. The truck has a mass that is 12 times the mass of the little car. It's a very little car. And the other thing I didn't tell you was that the truck was going very, very fast. So, which is going to exert the bigger force? The truck, clearly. Your gut just tells you the truck would exert the bigger force. However, if I go back to this operational definition of force, and in this case we have a pushing force, so I picked up the bathroom scale. Suppose that I am just a bystander that happened to witness this accident, and being of a scientific bent, I happen to quickly slide this bathroom scale in between the two, right as they collide. And I had enough presence of mind to read that there was some huge reading on this scale. Okay? Now suppose that the whole thing had happened over again, kind of like that movie Groundhog's Day, where you're forced to relive everything over and over and over again. But this time, instead of sneaking it in here to see how hard the yellow car pushed during the collision, this time, as I knew the accident was going to happen, right? Second day I lived through it, I slide it in this way. And what's it going to read the second time? Yeah, before we said that it really didn't matter which way I put the scale in, it would have the same reading either way. And that is Newton's third law. That if I hit, going back to that violent example of me hitting Chris, if I hit Chris's chin hits me. Now I told you that I really didn't like this phraseology of, for every action there's an equal and opposite reaction. Because that gives you the impression that when I hit Chris's chin, she gets ticked. She gets steamed. She boils about that during all of class. After class, she's waiting in the hall for me, and she's ready, and boom, there's a reaction. That's not what Newton was talking about at all. This action-reaction, it's impossible to say which one's the action and which one's the reaction. They both happen at the same time. While my fist is hurting her chin is hurting my fist at the exact same time. And Newton claimed that those two forces were exactly the same size. I don't know, do you believe that, Chris? That my fist hitting your chin is going to have just the same force as your chin hitting my fist? I mean, Newton's dead.
My gut feeling is no.
Your gut says no, doesn't it?
He'd be like moving and I'd be sitting and have a
Your gut says no. And so you had a question, Jasper?
But I'm just trying to, like, the car's going to get hit
Mm-hmm.
Doesn't that account for something? When I think of equal to that, I'm thinking, well, there's an heavy band like that, sit there. And I think of equal, and that's,
Okay.
I'm thinking mass, I guess, then.
Let's hold on to that thought. This law of Newton's, for the longest time, was the hardest thing to conceptualize because you really couldn't, you had a hard time testing it. You just kind of had to take it on faith. But recently, we've been blessed with some wonderful probes, and these probes allow you to very, very simply measure force. And let me just show you. Whoops, I want to cancel that. What this does is, as I push on that one, you can see that every time I push, you get a reading. Push on the other one, and every time I push, I get a reading. And what I can do with this now is I can do that experiment with the car and the truck. I can collide these two together, and then I can just actually measure which one exerts the bigger force. And so let me see, I'm going to need some help with this. Holly, could you come help me? When I ask you to, would you click on this mouse button and essentially push that collect button there? Mm-hmm. Okay. First of all, why don't you do it while I just push these together? Why don't you hit collect? Okay, now I'm just pushing those two together, and you see that one of those probes is going up, indicating it's a positive force to the right. The other one's going down, suggesting it's a negative force to the left. That's not important. We knew that one would be pushing to the right and one would be pushing to the left. The thing that is important is that, fairly close, given the level of sophistication of this cheap device, you get something very similar for the two forces. But of course, I was pushing kind of the same. Let's do this again with a collision. And tell me when you've hit the button. Okay. Now, let's, that's hard to see. So what we're going to do is blow that up. And sure enough, what you see is something that is very much the same. Now, again, that was two Volvos colliding with each other, and they were going about the same speed. So let's make this different. Let's suppose that this one's the truck. I can still get in there. Yeah, it's off the track. Okay. And this time we're going to bring the Volvo in and collide with the truck. Okay. Well, that's interesting. Let's go to unzoom and do that again. Why don't you hit collect and we'll do this experiment again. Okay. Let's zoom up on that. Oh my. See how beautiful that is? It was just a year and a half ago that we were able to do this experiment, and Jeff Adams and I were doing this lecture together. And we'd been trying to help students see this equal and opposite force for years and years. And finally we saw this, and it turns out we saw it for the first time during a lecture because we kind of thought of doing it right before class. And the two of us, the class just went on, and the two of us were just kind of standing here just, it just makes you want to weep. In truth, physicists are emotional people, okay? In truth, there is nothing I could do. I could make the truck ram really fast into the Volvo. I could do any possible experiment. Let's try that one, the truck into the Volvo. Okay. Let's see. First of all, we want to zoom out. Okay, and now we'll do collect. Okay. And this is going to be the most beautiful one yet. Voila. Ooh, yes, that's precisely the correct response. Ooh. Thank you, Holly. Okay. So the answer to your question, Jasper, is that yes, the car is going to be thrown. The truck, if it's a big loaded truck, is going to hardly notice. But the force that they exert on each other is going to be the same. As we measure it over and over again, we keep finding this result. Question, Gianna?
Yeah. Well, if you have acceleration equals force over mass, right? Okay, if you have the acceleration at 50 miles per hour, if you have your acceleration of that, and then you have your mass is greater, then why wouldn't it be the same? Like if you did that for both the Volvo and the truck, you would get different forces.
Okay. The trouble there is the cause and effect. I do have F net equals ma, but this equal sign means something much, much more than just they happen to have the same number. This equal sign here means causes. And so that's the thing that is what causes the other. The force is what causes the acceleration. And if I have the collision between the truck and the car, I'm going to call this the truck acting on the car, using the notation that you used in tutorial yesterday. This one I'm going to call the car acting on the truck. Newton claimed that these two had to be exactly the same size. Now, the force that acts on the car is going to take the mass of the car and accelerate it. The force that acts on the truck is going to take the, how should I draw this? Yeah, the mass of the truck and if this force and this force, as Newton claims, are really the same size, what does that tell me about the acceleration of the truck? It's got to be very, very small. And so your assumption that the truck and the car have the same acceleration can't be consistent with Newton's third law. That's correct. But it's the force that causes the acceleration. And indeed, this predicts that the driver of the truck doesn't feel much of a jolt, doesn't feel much of an acceleration. The driver of the car finds his or her velocity change drastically. Okay? So the it performed an illegal operation. That's not good. Pinball machine? Oh, okay. Now, in that case, the plunger stops very suddenly. That's a large acceleration. Okay. It doesn't necessarily have to be going the opposite direction. Going from very fast forward to stopped forward is still a very large acceleration in the opposite direction. Okay, excellent question. This is the way I prefer to talk about Newton's third law, and this is the way I wish Newton had said it in his original text. If a red object pushes on a blue object, the blue object always pushes back with a force that is equal in strength and opposite in direction. That's why it's equal and opposite. The part that's equal is the magnitude. The part that's opposite is the direction. Again, when I hit Chris, one of those forces, the one on Chris, is that way. The one on my hand is this way.
Why isn't it displacement factor anymore? That's why, the gut feeling is that the truck would have a bigger.
Displacement?
Right. Why isn't it?
The little car has a much greater acceleration, and so its velocity changes. If it were at rest, it changes very drastically from being at rest to, suddenly being thrown some very fast speed. So it's built into Newton's second law here. The truck, on the other hand, because its mass is so big, has a very small acceleration. And so if it started out going 100 miles an hour, after the collision it may be going 99. It didn't change very much. But yet the car gets thrown. And how far it gets thrown, I have to use those kinematic equations of chapter 2. But the acceleration that gets entered into that list of variables comes from here. Yes, Gordon?
I have a question. Besides, like the trailer brakes they showed in the book here, acceleration, somehow I'm getting that gut feeling that it's like really important.
Mm-hmm.
How else do we use it? I mean, what applications come out of this using the acceleration?
Using Newton's third law or using...
Well, I'm just seeing acceleration here as something, mass is kind of set, and the force is the relationship between the mass and the acceleration. The acceleration seems to be this factor that has a great deal to do with what happens. So besides the trailer brake application, how else do you use it?
Well, physics at its basic level is just a study of how things move and the forces that cause that movement or the change in movement. And so the acceleration is just kind of the ground floor. I find that so many people don't understand Newton's second law, the F net equals ma, because when they were studying acceleration, you remember you all started out thinking that acceleration and velocity were very similar concepts. And on that pretest, you drew arrows to represent acceleration that really were velocity vectors. And so my feeling, if I tried to give you a feeling that acceleration was all important, it wasn't so much because there were day-to-day applications that you could point to, like the trailer brake, but because everything else in physics is built upon that concept. We can't correctly understand the forces until we understand we have a correct understanding of this acceleration that the forces generate. And so I think it's more as a building block that it's so valuable.
I like to try to
Harness things, an entrepreneur here. Well, I'll try to think of some more examples like that trailer brake example. In the truck and the car collision, what we would do if we wanted to draw free body diagrams for these, we would have to draw separate free body diagrams. And for the red car, there would be many forces on the car, but one of them would be a normal force, a push, that is the blue object on the red object. And what Newton said was that over on this other free body diagram for the blue object, the truck, there would also be, this is important, if this one's a normal, a push, a perpendicular push, this one has to be a normal. They always come in the same flavor, okay? And if this is the blue object pushing on the red object, the simple way to find the companion force is to switch those indices. And now we have the red object pushing on the blue object. And so at its most fundamental level, what Newton was saying is that forces don't come one at a time. They come as matched sets. You will always see two forces appear at the same time. They will be equal to each other. They'll be pointing in the opposite directions, and they'll be acting on different objects. If one of them's acting on the blue object, the other one will be acting on the red object. And they're a matched set, a marriage. Okay? Marriage. Now, I got to tell you a quick story. A little bit of knowledge is a dangerous thing. I teach my children Newton's laws at a very young age, thinking it will make them better people. And I remember one day, my youngest, who at that time was like 5, Matthew, came running into the room, just crying, just bawling, you know. He just, Josh hit me, you know. And Josh, who at that time was in high school, comes running in right behind him, wanting to cover his side of the story. And he just said, well, Matthew hit me too. And Matthew, you know, the young one's just incredulous, just, I did not. My older son said, yes, you did. Newton's third law. He still got into trouble there. It was a nice try. But, okay, let's do something with this. Let's pretend that we're rocket scientists. And we have a rocket that we built, and it looks like this, that I mentioned I can't draw. And we put that rocket on a great big slab of concrete pad. And then we have the countdown, 10, 9, 8, 7, 6, whatever. And we get to 1 and we blast off and fire, different color fire. And the thing lifts off, and it looks kind of like that. So that's what I was trying to draw. Okay? Now the question I would ask you is, this thing is accelerating upward. It's being pushed up into space. And the question I would ask is, what thing, what object can I blame this force on? What thing is actually pushing that rocket upward? What? I'm sorry? Air? Gases? What? Any other ideas? I'm sorry? Tax dollars. No. No. Thrust? That's an idea. I want a thing, something I can taste, I can smell, I can touch. Launch pad? Okay. Concrete launch pad. Let's look at that idea for a second. This concrete launch pad pushes the rocket up. Let's ask this question about that push. Is that push going to be a contact force or a non-contact force? Well, it's contact force when I got it sitting on the pad right now, but as it's left the pad, it's no longer touching the pad, so how can I have a contact force between the pad and the rocket if it's okay, so maybe it's that gas that's pushing on the pad, and it's the rocket pushing on the gas and the gas pushing on the pad. Okay? hold that thought. Hold that thought. And what we're going to do is we're going to, let's see, I'm not going to need those anymore. We're going to create ourselves a rocket, and I would like you to hold on to this and make sure that it doesn't get blown all to smithereens. I'll just put this in here. Okay, this is our rocket, and this is the engine. Ah, yes. This will be fun. Okay, now, folks, safety first, okay? Okay. What I'm going to do is blast across the room here, and it's important to be aimed right. It's also important to be coordinated. I don't know, you might want to move, Holly. Are you okay? It's important to be aimed right. Now, the first time I did that demo 7 years ago, we were over in Reed Hall, and I was coming up very fast, faster than I thought I would, on this brick wall. And so I turned around to use the air brakes, and I forgot to turn it off as I turned it around, and I took out the front row. You know, just pages and books going all over. So the question I have for you is that I very quickly left the place where I had this launch pad, and I was just scooting along. What if I were to do this experiment? What if I were to close that door and suck all the air out of this room? You know, we all take a big breath first. You know, and we do this experiment again, and I blast off. Would I go anywhere? At first I would, and then I wouldn't. As long as I was pushing against that, then I wouldn't. Okay. Everyone agree?
Definitely.
Mike?
Yeah, definitely. It starts with constant acceleration.
Okay. But what about when I get over here? Would it still be pushing me? Yeah, of course it would. Because I mean, you saw the movie Apollo 13, and they're up in outer space. There's nothing to push against. There's, you know, just like if we sucked the air out of this room, and they still were, you know, jetting along. And so the stuff that you push on is not the important thing. The concrete pad has nothing to do with it. The concrete pad just keeps the rocket from sinking in the mud. Okay? What is important here, as Adam pointed out right up front, was the exhaust fuel, the fuel exhaust. This rocket essentially is taking gas that's inside of it and throwing it really fast that way. Newton says that if I throw something that way, it puts a force back on me and pushes me this way. Okay? So the interaction, it's always a dance between just two things, never more, just two. The rocket pushes the fuel pushes the rocket. Now, I didn't understand this as a young man, and when we were growing up, we did a lot of experiments. In Southern California, there were tons of frogs, and so they tended to be our helpers. And the frogs never got hurt in the experiments, but the experiments often involved rockets. And they had rockets at that time that were these little capsules with heat fins and an exhaust port, and you can open this up and put a solid fuel in there, and then you lit the fuel and it would blast out. And we would do many experiments where there would be a can attached here with an astronaut inside, and those astronauts would jet along a string between my house and Paul Jonke's house. And it occurred to me that we were really losing out because we very quickly lost our launch pad to push against. And so I, being the genius that I thought I was, designed and made a flying saucer. And what I did is I took one of my mother's pie plates and I attached it to the rocket like this. And then, so that I could always have a launching pad to push against, I took a second one of my mother's pie pans and attached it to the first. Oh yeah, call it what you will. Adam calls it a bomb. And yes, indeed, that's what it turned out to be. Okay, in my teenage head, I was thinking, this is going to be great because I'll always have something to push against. And indeed, it just blew itself apart. Okay. Now, yeah, just doesn't work. Just doesn't work. You're sure you're okay?
Yeah,
okay. Sorry about that. Let's review with this example. You're stuck in the middle of a frozen lake, and it's a perfectly frictionless pond of ice, and you're holding a large bag of gold. The surface is perfectly frictionless. How do you get off of it? Gordon. Ah, a businessman. You know, Jeff and I were, putting this lecture together, and Jeff posed this question, and I immediately said, well, gee, that's easy. You take the bag of gold and you throw it. You know, and he looked at me with this sad, sorry look on his face, like, no wonder you are so poor. You just take off your shoe and you throw the shoe, and you just keep on throwing stuff. What's the difference between throwing the whole bag of gold and just throwing one bag of gold? Oh, no, did I say that? What's the difference between throwing a whole bag of gold and just taking one coin of gold out and just throwing it? What would be the difference in the result? Yeah, I'd have more gold in the end of the day. But what about getting off the ice? Would I get off in both cases? It'd take longer in the one case. Okay, throwing the whole bag of gold is going to exert a larger force on me, give me a larger acceleration. I'll get going faster, and I'll scoot across the ice faster. Okay, but if I'm patient, I can keep all that gold. Okay. Yeah. Eventually, if we wait too long. Okay. Now, let's look at this problem here. Gary has a major problem. After studying Newton's third law in his physics class, he has convinced himself of its validity. Unfortunately, he has convinced himself while sitting in a closed room with a single door. He reasons to himself, if I push on that door to go out, Newton's third law tells me that the door is going to push back with an equal force. That force is going to cancel the force that I push with. Even if I push as hard as I can, that door is going to push back just as hard. Oh no, I'm stuck in this room. Why did I ever take physics? Okay, some of you have had that feeling. Why did I ever take physics? What's wrong with Gary's reasoning? Let's help him out here. Mike? Okay, so let's suppose that we consider that friction. Let's consider that there's friction between Gary's feet. He still pushes on the door, and because of Newton's third law, it still pushes back just as hard. So why would the door open? Just because there's friction. But there doesn't have to be. If I grease down the door, I can still open a What's that?
Would be the amount of friction, whichever one had the most friction would stand still.
Well, let's go another direction. Let's say that this was a frictionless classroom. Let's say there was no friction on the floor, but Gary just happened to be standing close to the door. If Gary hit the door, I mean, he's going to go flying, but in the process, would the door open?
What would happen to the truck and the car when the big truck, like with, it has more force to begin with, they hit and some amount of force, the car's displaced from it.
Okay, but let's ask this question. With that truck and that car, we said those forces were the same, so why don't they just cancel each other out? One's going this way, one's going that way. They're the same size. When they just add up to zero?
Because they have the same force, the force doesn't act equally on both objects.
They don't act equally on both objects. Okay, the force is the same on both objects, but they don't have the same effect on both objects. Okay? But why don't they cancel, I think, is the question I'm asking. I mean, you're saying that one has a greater impact on the one object than the other, but why don't I just add the two forces and get zero?
Because the mass is,
Let's say the mass of the door is exactly the same as the mass of Gary.
then they probably cancel out.
Cancel out and the door wouldn't open? That's a word we haven't operationally defined. We're going to hold on to that one for a while. Remember that diagram that we had with the collision between the truck and the car? There were two free body diagrams. One for the car, one for the truck. And the only force, there were two forces, but one of them was acting on the car and one of them was acting on the truck. And if I want to know about the motion of the car, how it gets thrown, I only have to consider that force that was exerted on the car. I don't have to worry about what force was acting on the truck. That's going to damage the truck. Only the one that acts on the car damages the car. And so even though there's two forces, equal and opposite, they never act on the same thing. One of those is causing an acceleration to the door, causing it to open. The other is causing an acceleration or a force on Gary, and if there's no friction in the room, it's going to cause an acceleration of Gary back the other way. They can't cancel because they don't act on the same object. Hello, guys. How are you? What's that? It's working great. Thank you. Thank you. Okay, let's do this experiment. Perhaps you did this in class. Let's take this book and drop it. Now, if that's say a 5-pound book, then what that means is that the earth is pulling on that book with a force of 5 pounds. Okay? And that's what causes the book to race down, hit the ground. Now, Newton said that if the earth is pulling down on that book, 5 pounds worth, that what has to happen? Yeah, the book is pulling up on the earth, but how big? The same or less? Less. How much less? Much less. Now, Linda, Newton said they were the same pull, but again, he's dead, right? So maybe he was just confused and dead. Okay. So is the pull on the earth the same 5 pounds that the earth is pulling on the book? Yes, that's the same. They're each pulling on each other 5 pounds worth. And we know that pulling 5 pounds on this book is enough to accelerate it downward 9.8 meters per second every second. What's that same 5 pounds going to do to the earth? Next to nothing. I mean, it's huge. Its mass is so huge. Okay? This is a famous question that always shows up on standardized exams. This is, let's come back to that. This is the famous bug problem. Okay? A bug splats on the windshield of a car moving at 100 miles per hour. Which feels the greater force, the car or the bug? Which would it be according to Newton? Have to be exactly the same. Okay? And this is where we get confused. Which has the worst day? Okay? That's the difference. The force is the same. But what we get wrapped up in is, well, man, the bug's messed up. You know, it just had a bad day. The effect is not going to be the same. The acceleration's not going to be the same. The force is going to be the same. Now, let's talk about a simple Coke can sitting on a table and draw a free body diagram for that. The first force that I would put on there is the weight force, and that's an interaction between what and what? How do I label this according to your tutorial? Earth pulling on the can. Now, some folks are tempted to put gravity pulling on the can, and that's going to get us into trouble because of Newton's third law, and I'll show you that in just a moment. Now, what other forces are acting on the can? Normal force, table on the can, and you notice that I drew that arrow the same length as that weight arrow. And so I would now ask the question, those two forces are equal and opposite by what law? By what law are those two forces equal and opposite? Second or third? That's where all the points are on the next exam. You're going to have to justify why two forces are equal and opposite. Are they equal and opposite by the second law or the third law? I'm hearing second, I'm hearing third. Okay, if they were equal and opposite by third, they'd have to be acted on different free body diagrams. They would also have to be the same flavor of force. If one's a gravitational force, the other would have to be a gravitational force. And if you look at this can, but look at it in a different situation. Let's say the can is sitting on a table, but the table's inside an elevator. And the elevator is accelerating upwards. You went in on the first floor and you hit number 10. Okay? What's going to have to change in that free body diagram? Does this force change, the weight force? No, the Earth doesn't care what the can is doing today. It's going to suck down the same amount on that can. So what has to change? Yeah, that normal force, in order to give me an acceleration upwards, has to increase. And so those two forces are no longer equal and opposite at all. Okay? So I would ask, Gordon?
I have a question now. It's kind of like the same thing with the magnet. I say that it's now, because it's in that elevator, and the elevator is what's going up, that the force is the elevator now, and not the table.
Is that a contact force or a non-contact force?
Contact.
Okay, but the elevator's not touching the can.
Through the table.
Well, you're going to make life very complicated for yourself if you have to keep on going back to the root of every force. It's much simpler just to say, there's the weight force, are there any magnets, and then what is physically touching this can? And you'll find that'll simplify these problems a great deal. No, just concentrate on what's touching that can. Okay, now the question I would ask is, what's the third law companion? Newton said that for every force there's a companion force, equal and opposite. What is that third law companion force for the normal force, the table on the can?
The normal force of the can.
Yes, okay. I find it by first of all noting that if this is a normal force, the companion force has to be a normal force. I take the indices, table on the can, and I switch it. Can on the table. And I have to find that force where? On a free body diagram of what? Of the table. I have to draw another free body diagram for the table, put the normal force there. It's the same length as this force, but opposite direction. And to show that they are companion forces, these tick marks don't just mean they're the same size. They mean they are part of the same interaction. They are always going to be the same size, regardless of how things change around them. Okay? What about this force here, the gravitational force, Earth pulling on the can? What's the companion force to that? can pulling on the earth, and what free body diagram would I have to draw there? The earth, and that's a messy free body diagram. That's got billions and billions of forces on it. I just happen to draw one of them. That's the can pulling up on the earth, same size, opposite direction. And I'm going to use 2 tick marks because I've already used one to represent that companionship. I'll use 2 tick marks here. Okay? Question?
The can is what level the can is so small compared to this, or how can I have an equal for this has equal velocity?
Yeah, it turns out we're
Just because of the mass of
right. Again, with the bug problem, the effect is not going to be the same. They're both pulling on each other with about half a pound, but that half a pound does nothing for the Earth. Okay. Now, if I go back to the situation where the acceleration is 0, what happens to this this set of diagrams? Well, these 2 don't care. And what about these 2? Yeah, they go back to being shorter. And now this one's the same length as this one, but I don't use any kind of special tick marks to represent that. That's not important. The tick marks represent the fact that these are a companionship. Now, I need just 2 minutes for a little story. When I first arrived here, I was asked by a grad student to serve on his doctorate. He was just finishing up his doctorate. And he needed 5 professors to serve as a committee for his defense. And he picked me because I looked like I would be easy. And so he went through his defense, and he was answering all of these very complicated questions. He was brilliant. And right at the end, the professors in the room, the other professors, turned to me and said, "Well, Greg, you haven't asked any questions." And I said, I'll call this fellow Bill. It's not his real name. I said to Bill, I said, "You've got a Coke can in front of you. Draw me a free body diagram for that Coke can." And it suddenly got very quiet in the room. And the professors were suddenly embarrassed that they had invited me to be on their faculty, because this was a doctoral level exam, and this was a freshman physics sort of question. And this grad student, I called him Bill, he looked at me with kind of a look of disdain and went to the board and he put weight down and normal up. I said, "Bill, you've drawn a normal force up. Newton said for every force there's an equal and opposite force. What's the force that's the companion force to that normal force?" And he looked at me like I was stupid, and he said, "Well, that one." And suddenly the other professors in the room were starting to take notice. I was, whoa. I said, "Well, Mike, why don't you just reach over there and push down on that can? What happens to your free body diagram?" He says, "Well, I'd push down, and this normal force would get bigger." I said, "Well, Mike, you told me that the normal force and the weight were third law companion, equal and opposite. They're not equal anymore." And he says, "Oh, but these 2 are equal to that." I said, "Oh, so what Newton really meant was for every force there's an equal and opposite group of forces." And at this point he started sweating. I said, "Well, Mike, let's stop pushing on the can. Let's instead pretend that this whole room was an elevator and we were accelerating up. What would the free body diagram look like then?" He says, "Well, there would be the weight down and the normal up. Those are the only 2 forces, and this would have to be bigger to give an acceleration up." I says, "Well, wait a minute, Mike. They're not equal and opposite." And he said, "Well, that's because Newton's third law only applies when you're not accelerating." And again, it was very quiet. And I looked at him and I said, "Mike, your dog will die. your kids will move away, but Newton's third law will not stop working. It always works. And you know, he passed his doctoral level exam, but he had a very strong talking to by his professors, his advisor, about Newton's third law and how basic it is. So what I'm trying to get across is that this law is one of the least understood laws in physics, and yet it is one of the most basic and simple. Okay? We'll see you this afternoon.